Hello, it's Keith here, and this is lesson 9 of the platform-specific series of my Z80 programming tutorials. Now, if you caught last week's lesson, we had a look at how to use the Tilemap on the Master System and Game Gear, and we used them to create a Hello World message and a little sprite of our Tubico character. Now, this week we're going to use the same code to do the same job on the Game Boy Color and Game Boy, and we've got some similar Tilemap code that works in almost the exact same way for the Game Boy and the Game Boy Color, which is why we can use that same basic code on both systems. Now, of course, the Game Boy and the Game Boy Color don't use a true Z80, they use a GB Z80, so there are some slight differences, and that has been reflected in today's code. You'll notice some slightly odd things in there, but we'll have a look at those as we discuss the code. Now, you can see the example running here on the Game Boy Color, but we can also compile it for the Game Boy, so I'll just show you that now. I just change this to Game Boy. So now this is the same example running on the Game Boy, and it's just using a simpler palette, but it's the same bitmap sprite here. It's the same bitmap tilemap, sorry. It's not really a sprite, it's a bitmap displayed with tiles, and the Hello World message in the same font. So it's basically the same code, just with some modules swapped out that deal with the extra Game Boy Color features, but basically the same code. So let's make a start and let's have a look at the code we're going to be looking at today. So we had a look at the Master System and Game Gear last week, and the big difference between the Game Gear and the Master System and the Game Boys is the fact that the memory is laid out differently. The Master System Game Gear, they have a VDP, which is a separate graphics chip, and that has its own separate memory, so we access that memory without commands. But on the Game Boy and the Game Boy Color, it's much more like the Amstrad CPC and those kind of systems, where the graphics memory is actually memory mapped within the normal Z80 addressable range. So when we write from the area 8000 to 9000, we are defining the patterns that make up the tiles that we have available to us. 9000 to 9800 is a special set of tiles which are used only for certain circumstances. There's something called the window on the Game Boy, which is a overlay, a very crude overlay used for statuses and inventories and things, and those are extra tiles for that. And we have two tile maps. Now, I believe there's two, so you can flip between them, but we're only going to use the first one between 9800 and 9C00. So we'll be writing the definitions of our tiles, including the font, to this range here, and then we'll be using this range here to define our tiles in the tile map. And the tile map is 32 byte wide, and each byte is the number of the tile. So if we wanted to put tile number 255, we just locate the line by moving through the tile map. Because we know each line is 32 bytes, we just need to move 32 times y plus x, write the tile number we want, and that's it. There are some extra features on the Game Boy Color, which we're also going to have a look at. The Game Boy Color does have some more advanced features. Firstly, it has color palettes. So although both systems are basically 4 colors per tile, we can have different palettes available to us on the Game Boy Color, which we don't have on the Game Boy. And there are some other functions as well. You can flip tiles, and you can change the priority of the tiles, so the tiles go in front of the sprites. But the important thing to remember is if you're trying to write a game that runs on both systems, that's going to be very difficult for you because those features simply don't exist on the basic Game Boy, which is part of the reason that some games only work on the Game Boy and some work on the Game Boy Color. Now, if you are using the Game Boy Color, the definitions for the tile map and the extra 256 tiles, because the Game Boy Color has 512 tiles, are actually in the same areas. So there is a command we'll look at later which pages in an extra bank of memory, and so the tiles 256 to 511 are here, and then the extra byte of information for each of the tiles is in the exact same position here, and we'll have a look at the format of that later. So if you didn't catch last week's lesson, we're going to have to discuss bit planes now. If you're familiar with a system like the MSX or the SAM Coupe, you'll know that when you're defining colour on those systems, the 16 colour palette is basically each byte of data defines 2 pixels on the screen, and one nibble defines the first colour and one nibble defines the second. Not quite as neat on a 16 colour system like the Amstrad CPC, but either way, 1 byte defines 2 pixels worth of colour. Now, on the systems like the Game Boy and the Game Gear, it's actually different. Each byte defines 8 pixels, but it only defines 1 bit of those pixels. So if you think for a moment of a 16 color system, then each byte will define all 8 colors of 8 consecutive pixels. And then the first byte we write to the memory, will define the first bit, which is either 1 or 0, the value of that bit. The second bit is 2 or 0, depending if it's set or not. And then 4, and then 8. So we make up our colour from 0 to 15 from 4 consecutive bytes that make up these planes of bits. I don't know if that's a little difficult for you to understand, but I'd suggest if you are a bit confused, maybe just play around writing some data to the memory, but hopefully it'll become a little bit clearer as we look at it later. But if it's not too clear, don't worry, because you can always use my sprite editor, which has export functions to export the bitmap that I'm showing in my example today to all of these systems, and that's how I actually created the Hello World Chibico sprite on all these systems, because it can convert to the required format for whatever machine you're working on. So I've been describing a 16 colour system just for convenience, because I can compare it to the MSX, but of course the Game Boy and the Game Boy Color are only 4 colour systems. Irrespective of which system you're using, you're only defining 4 colours per tile. That means there's just 2-bit planes, because we're looking for a value from 0 to 3, and that means that each 8-line tile will have 16 bytes in it, and this means we can work out the position of the tiles by multiplying the tile number by 16 and then offsetting that number from memory address 8000, and you'll see that in action later. So hopefully we've had a bit of an introduction to bit planes here, and this is the example we're going to do here. The colour definitions are different, but we're going to have a look at those in a later lesson. And as I've said, if you want to try to make your own bitmaps, you can use my sprite editor, my Accu sprite editor. Just go to the Game Boy memory menu and select Save Raw Bitmap, and that will create a file in the format that the system needs. But just bear in mind, it has to be, for this example, 48 by 48, and it does definitely have to be 8 by 8, a multiple of 8 by 8 pixel square, because the tile maps are 8 by 8 pixels. So just something to bear in mind if you're going to try this yourself. So anyway, let's have a look at our actual source code today. So this is the basic core example, and this works on a wide variety of systems, including last week's Game Gear. It's completely unchanged from last week. Also the Game Boys, and it works on the MSX, MSX1, and also MSX2, ironically, and we'll be having a look at those later. But as I say, we're not going to look at this in too much detail, but essentially all it's doing is it's using a print string command, which is compatible with our normal one. Then we are selecting a tile number here and a memory address. We're filling in those tiles. We start at tile 128 and we load the Chibico data in from this memory address here, and that's because we've loaded in the hardware specific bitmap that we exported with my Accu sprite editor here. And so whatever the system we're working with, that will get the right data for that system. We then define the tiles, and that moves consecutively through all of the tiles from 128 onwards until all the data is used up. Then we want to draw those tiles into an area of the screen so that the Chibico character will appear. So we're starting at 3,3, and with the tile map is 6 by 6 tall and 6 wide, and that's what we're doing here. And the first tile in the tile map that we want to show to the screen of that Chibico sprite is tile number 128. You can see it's also here. As I said before, the tile map starts at 8,000, and each tile is 16 bytes wide, and so we can work out where the memory address to write to by multiplying 128 by 2 by 8 and then adding 8,000, and that will select the correct memory address for us to actually write the sprite data to the tile we want. So that's nice and simple. It may look a little bit confusing, but I'm sure if you have a play with this, you'll come to see how it works. So the commands we're going to look at today are the define tiles function, which will create the pattern data of the tiles, and then the fill area of the tiles command, which will fill a grid area with consecutive tiles so that we can get that Chibico bitmap onto the screen. Because if you remember, the problem with the Game Boy Basic, the Game Boy Color, this isn't a problem, but if we're going to support both, it is. It's got only 256 tiles that it can show, but it would need more than that to show completely different bitmap data on every pixel of the screen. So we have to compromise a bit, and the way I'm doing it is I'm filling an area with consecutive tiles and then setting those tiles to the Chibico sprite so that we've got effectively a bitmap here. But all of these blank areas here are all tile 0. So that's the way we're emulating a bitmap screen on this tile-based system. Okay, so let's have a look then. So the first command we're going to have a look at is copy to bit. Let's find that. So here it is, and this is used by the initialization routine to load in our bitmap font. Now our bitmap font is the exact same file that we used on the ZX Spectrum and on all the other systems. So each byte contains 8 bits that represent 8 pixels, and each pixel is only 2 colors. So because of that, we need to load this 1 bit per pixel bitmap into memory. Now, I said about the bit planes, and each pixel on the screen is represented by 1 bit of a byte in the first bit plane, but then also the second bit plane, and those two are added together. So we're loading in the bitmap from HL here, and then we're writing it to the destination, and we're doing that twice. So the first time we write them, we're setting bit plane 1, and each bit will effectively have the value of 1 or 0. And then the second time, we're writing the bits, and they will effectively have the value of 2 or 0. So added together, we're setting all of the pixels of the bitmap to 3 or 0. So this will have the effect of setting the font to color 3. And that's what we're doing on all of the systems now. These examples all set our black and white font to the highest color in that system. So color 15 on a 16 color system, or color 3 on a 4 color system like this. So that's our kind of common rule now that we're using to make the systems all common. And this was something that came in with the Grime Z80 project. I should point out Grime Z80, which is my ongoing 7-day programming project to make a game on 11 systems, was based on this example. This example was kind of the template. It was improved and reworked a bit, and that became Grime Z80. And I think if you're looking to do a programming project on a lot of different systems, or even if you're not possibly, Grime Z80 will be a great starting point, because you've got basic graphics in the form of a tile map, you've got basic sound, basic joystick control, and it's a nice little simple thing, and I managed to get it working on all these systems in 7 days. So hopefully if you're just starting out and just want to get something working, you'll find it pretty easy too. Well, anyway, so what we've basically got here is a command that loads in bytes from HL, writes them to 2 consecutive memory locations in DE, and repeats for the loop of B and of BC. Now, apart from writing the bytes twice, this would be very similar to an LDIR command. You've got to bear in mind that the GBZ80 doesn't have an LDIR command, so that's something that will catch us out. But it does have something quite interesting. It has an LDI command. This isn't the load increment command that you might be familiar with on the Z80, which just misses the repeat. This is a special Game Boy only command. What it does is it loads in from the memory address HL into A, or can also write. It can do it the other way, but it automatically increments HL. So the equivalent, if we wanted this to work on a Z80 system, would be to do that, and that would have the same effect. But this LDI command is faster on the Game Boy Z80, and so because this code is only going to run on the GB Z80, I'm using this LDI command because, again, as I've said, on the Z80 systems there would be cases where we wouldn't need to run such a clunky command as this, so let's use those faster Game Boy Z80 commands while we've got them, because we need to make up for the lack of things like LDIR. So this is our 2-color copy bitmap command, and that's all it does. All it does is the fonts basically. And so next we need to define our tiles, and this is how we get the Chibico bitmap from the file into video memory so that we can show it later. So let's have a look at that. So here we go. Now this really is basically an LDIR command, but as I've said already, Game Boy doesn't have it, so we have to fake it. So again, we're using the Game Boy Z80's LDI command, which is the special load A from memory address HL, inc HL command here, but it is faster than those 2 separate commands, so let's use it. There's no load LDID, it only works with HL. So like a lot of commands on the real Z80, HL kind of has all the power and the other registers don't have so much. So that's what we're doing here, and then we're increasing, we're just looping around BC until we get the end of our loop, and that's just copying our data from the memory into the tiles from tile number 128, which we defined as the destination using this calculation here. As I said, the Game Boy and the Game Boy Color use the same memory locations, so we don't need to do anything clever there. So once we've defined our tiles, we need a command to actually work out where we're drawing things. By drawing things, I don't mean lines or bitmap data, I mean drawing tiles. So what we're actually going to write is tile numbers, because as I said, the Game Boy isn't a bitmap screen. We don't set pixel data, we set tile numbers. So we're going to have this get VDP screen pos, which is arguably a badly named function because the Game Boy doesn't have a VDP, but it's a common function name for all of our systems, so please bear with me on that. So this function works exactly the same as our locate command in our previous examples. It works on the basis that the top left hand corner of the screen is 0, 0 and that will be defined in BC. And in the case of this function, it returns HL with the memory address of the requested location. So the first thing we do is we swap B and C because we need them the other way around for our purposes here. And we start with this memory address 9800, and if you remember, 9800 is the memory location of tilemap 1, which is the one we're going to be using because that's the one that's shown to the screen by default. We don't use tilemap 2. So what we need to do is we need to shift B around a bit. Each horizontal line is 32 bytes, so we effectively need to multiply Y by 32, and then we need to add the X position, and then we add the result there to HL, and that will give us the memory location of the XY position that we requested here. And so once we've done this, we can just write the number of the tile that we wanted to appear at that position, and it will immediately appear on the screen. There's no delay. It's very, very fast because we're literally only writing 1 byte. And that's really the benefit of the Game Boy system. We kind of suffer a bit with the lack of flexibility with regard to it not being a true bitmap screen, but we gain with this incredible speed because we can write an 8 by 8 pixel square with just a single byte. So that's very nice. So that's our get VDP screen pos function. Now next we're going to have a look at this fill area with tiles function, and this is a simple function which is how we get that chibi code sprite on screen. Now if you look at the sprite, it's 6 tiles across and 6 tiles down, making 48 pixels by 48 pixels. And so here's this function here. Now you should recognize this because it's basically the same as our get VDP screen pos. I've just sort of unwrapped it into here to make things a little bit faster, but I could have just repeatedly called this. So what we're doing is we're loading in BC with the start top coordinate. HL is the width and height, and D is the start tile number. Now D effectively won't be used because this system only supports 256 tiles in the way we're using it, but for compatibility with things like the master system, I'm defining DE as being the tile number to allow for more than 256 tiles. And you could reprogram this and make it more advanced to allow it to use the Game Boy Color tile map, which is 512 tiles. I've not done that at this stage though. So you'll notice here we're using these defined memory addresses. These are defined in the Game Boy header, and effectively I'm using them to emulate the IXH and IXL registers. Another of the limitations of the GB-Z80 is it doesn't have IX or IY registers. In this case, I couldn't make do with just the basic registers, the BC, DE, HL. I needed a few extra temporary variables. So as part of my Z80 emulation, I've defined a few bytes of memory for all of the registers that the real Z80 has, but the GB Z80 doesn't. So in this case, I'm just using those temporary memory addresses as loop counters here. So that's what those are. And then really, it's very simple. As I've said, all you do is you write in the byte number you want to show on the screen, the tile number you want to show on the screen to HL, and we're just reading that in from E here. We can't do LDI HL, E, that doesn't exist. So we're just loading E into A and then loading A into HL and using this LDI, which is load and increment, as I've already described. So really a lot of code there, but very simple. Just fills a grid with tile numbers. And if you want to see what that looks like, effectively here it is here. So it just consecutively loads each tile on the screen with a consecutive number. And the real magic, if you will, is being done by my sprite editor, which is converting this bitmap into the tile numbers, into the consecutive tiles in the bitplane format, and that's how we get it done. And that's kind of the benefit of writing your own sprite editor. If I wake up tomorrow and want to support a system that I've not really worked with before, but it has a different format, I just need to write something that outputs the data I need, and then I'm sorted. So, and that program is open source, so if you wake up tomorrow spontaneously feeling like programming it to work with the Super Nintendo, then you're welcome to go ahead. So that's basically all of our functions that we're using here. They do all mimic as close as possible the same functions on the Sega Master System. They don't work exactly the same because, of course, on the Sega Master System we use outs, whereas on the Game Boy we're using HL and writing to memory addresses. So as I said, it's not quite identical, but it's close enough. And as I said, the basic code works on all of the systems, and the Grime Z80, the graphics code to a great extent, is compatible with all the systems, although obviously there are routines that are platform specific. So we're not really using the Game Boy Color tile options, but I do want to discuss them at this point. So the way you use them, as I've said, is there is a second bank of memory that the Game Boy Color exclusively has that fills this area, and it gives an extra 256 tiles in this area and an extra byte of information about the tile map in this area and this area. And well, what extra information is stored in that tile map? Well, here we go. So the first thing you have is a color palette number, and you've got palettes from 0 to 7, and so the first right-handmost 3 bits define that palette number. The example you're looking at on my system is all using palette 0. I don't actually set the palettes on here, but the Grime Z80 project does. So as I've said before, if you really want to see this in action now, just go ahead and look at the Grime Z80 project. But if you don't want to look at that, I'm going to be covering all of this in later lessons as well. So, you know, follow the channel and you'll see it sooner or later. Now, I said about the extra 256 tiles that the Game Boy Color has. The first basic byte of memory in the regular Game Boy's tile map defines a number from 0 to 255. You could imagine that the 8th bit is stored in this extra memory here, so that is effectively, if you want, the 8th bit, or alternatively you could think of it as the RAM bank number. So 0 would be the basic Game Boy's memory, 1 would be the Game Boy Color's exclusive memory. So that's how you select between the first 256 and the second 256 tiles. Beyond that, you have a bit that does absolutely nothing, for some reason right in the middle here. That's slightly odd, but there you go. Then you have vertical and horizontal flip, because you can flip tiles on the Game Boy Color, but as I've said, you can't do it on the Game Boy, so anything I'm going to do is going to work on both. So, you know, I guess if I want to flip tiles, I'm going to be storing 2 copies of the tiles. So anyway, as I say, if you wanted to do a Game Boy Color only program, then that would be a great function to have. Then you've got a priority option here, and that allows you to put a tile in front of the sprites. So if you wanted to have a tree go in front of your running character or something, that's what you do. But again, no equivalent on the Game Boy. So there you go. So that's basically it. Not quite as hard possibly as the Sega Master System, Sega Game Gear, because we don't have that VDP, but I say essentially the same function. And beyond this, we're now going to have a look at the next week. We're going to look at the MSX1, which is also a tile map system. It uses colours quite differently, but basically, as I say, very similar functionality on that system. And then going on beyond that, we're going to have a look at something a bit more different, which is the MSX2's VDP, which is not a tile map system, but I'm actually pretending it is. I've written a sort of emulator for tile maps, because while it's not a tile map system, it does like copying blocks of memory from one place to another. So it works better as a tile map system than as a bitmap system. So that's something we'll be having a look at later as well. So anyway, I hope you've enjoyed today's lesson. Please like the video and follow my channel if you want to see more. And of course, go to my website. All of this text is on there, and you can download the source code for today's lesson and all of the others from there as well. So thanks for watching today, and goodbye.